Welcome back. Here's a nice little voltage division problem. So we're given a circuit. We're given circuit right here. 75 volt independent source. So this is an ideal voltage source. That is, we're assuming that it always puts out 75 volts no matter what. That's ideal. In real life, voltage sources don't always do that kind of thing. Like a battery, the voltage will drop a little bit as the current changes. But this is a model, it's an ideal model. So we're using an ideal source so that we can solve it. Okay, so we've got a 2K or a 2000 ohm resistor R1 and then a 500 ohm resistor, and then we've got this reference voltage that we're interested in called V0, all right, which has this polarity. So we're interested in the voltage across resistor 2, and we're asked to find what is V0, what is the power in resistor 1, what is the power in resistor 2 at no load. Okay, and then it's going to turn out that the power in one of these guys is too much. So we want to resolve it. Okay, so we want to resolve R1 and R2 for power less than or equal to 1 watt. So what we're saying is we want to get the same V0 but with different resistor values so that the power drawn in each one of these resistors is no more than 1 watt, because a 1 watt resistor is a standard package. Let me say, so let's see, so let me rewrite this out. So standard 1 watt resistors with the same V sub 0. All right, that's another way of saying what we're doing up here, this section. Okay, you'll see. I'll talk through it as we're doing this. But a standard 1 watt resistor looks about like so. Has a little stripe. This is like actual size, maybe a little bit bigger. But this is a standard 1 watt package. Okay, if you want it, if you have a situation where all your numbers work out such that it's more than 1 watt, you need to buy a bigger resistor. So there's not only voltage and current in a resistor, there's the wattage that it can handle, right? And little bitty tiny resistors can't handle a lot of wattage because it's heat, and there's just not enough area for the heat to escape. But a giant old chunky resistor, could handle lots and lots of power leaving it. Okay, so let's start let's call this part A, really. This is part A, and this is like part B, I guess. Okay, let's solve this original part A. We have this open circuit across here, and what's the power on these guys? So this is voltage division. All right, so V0, just with our voltage division equation, is this source. This is let's call this V sub S. It's V sub S, this thing. We're interested in V0, so we put the adjacent resistor on the numerator, and the sum of the two resistors across there. That's our voltage division problem. So numbers, 500 over 2000 plus 500 equals 15 volts. Okay, so there's 15 volts across this open circuit with this configuration. And so we could use, we have a couple power formulas. We could use V squared over R. And if we know this is 15 volts, then we know this is 60, right? Because it has to add the 75. So we could use V squared over R for both of these using 15 volts and 60 volts. We could do that. That would work. The other thing you could do is find the current in both of these guys. It's the same current in both of these guys because they're in series, right? The only place the current has to go is through these guys. It can't go this way. That's an open circuit. So they have the same current. So let's just do that. So this is I. So by Ohm's law, I'd like you to narrate your homework like this with at least this. If writing a sentence out is better, then you can do that too. So Ohm's law is V equals IR, and so that means I is V over R. So it's going to be I is going to be the total I is going to be the total voltage over the total resistance. This voltage this voltage 75 volts is across the entire thing, and I is going over the whole thing. So you can use this, and this is 0.03 amps. Then we can do our power. So power in resistor 1, let's use I squared R. It's going to be 0.03 quantity squared times 2000. It's going to be 1.8 watts. So that's an answer. That's bigger than 2 watts. So using a standard 1 watt package, it won't work. This thing will melt or break at least, right? The power in resistor 2 is going to be 0.03. Same current. Resistor 2 rather. The same I is going through this guy. So let's use I squared R. So this many amps times 500 ohms is going to be 450 watts. Okay, that's part A. With the open circuit, there's just 15 volts, which leads to 1.8 watts in this resistor and 450 watts in this resistor. So this resistor is too much power for a standard 1 watt package. So let's say we still want the same 15 volts here, okay, but we want to resize these resistors so that they're drawing no more than 1 watt each. Okay, so that was part A. So we're going to resize the resistors, for less than 1 watt. Okay, so we still need V0 equals 15 volts. What does it say that? Yeah, standard. I'm sort of. I said that. I didn't write it down, but I said that. Let's think a little bit. So this resistor V0, or the resistor 2 associated with the voltage V0 has 15 volts across it. So the voltage at resistor 1, the voltage across here must be 75 minus 15. It's got to be 60 volts. As I've said earlier, this is a voltage divider. The 75 volts is dropped 60 across here and then 15 across here, which is a 4-to-1 ratio. Voltage drops 60 to 15 is a 4-to-1 ratio, which matches the resistor value ratio, right? 500 to 2000 is a 4-to-1 ratio. And the bigger resistor has the higher voltage, 60 volts. The smaller resistor has the smaller voltage, 15 volts. And we've already established that the resistor 1 has the higher power. So that's gonna be the same when we resize these guys, because it may not be super clear, but that's what's going to happen. So that's the kind of an insight, really, is that with new resistor values, this guy, the first resistor, will still have the higher power. Okay, and that's just an intuitive thing a little bit, but you can check your answer at the end to make sure that it actually works, and it will. So so I'm just going to write insight R1 uses more power. So size it first. Okay, so we have this formula. The power in R1 is, we have the V squared over R formula. So the power in R1 is the voltage in R1 squared over R1, V squared over R. So we can size R1 because we know these V, and that we're limited by the power. So we know that R1 is the voltage in R1 squared over the power in R1. Just solving this, just rearranging it, and we know that the voltage in R1 is 60 volts because it's the same 60 and 15 that we want, and the wattage we're limited to is the max wattage. So is 1, so it's 60 squared rather. It's 3,600 ohms. All right, that's an answer. And it'll draw 1 watt at that, which is our max. And then we can use voltage division backwards. We can use voltage division again, right? Because we know that this is 60 volts and this is 15 volts. So apply the voltage division equation again in here. And in other words, V0 then is 15 volts. It's also given by the voltage division formula, which is 75 times R2 over R1 plus R2, right? But we've solved for R1 already. So this is 75 R2 over 3,600 plus R2. Okay, so we're just taking the voltage division formula and putting the knowns, this is a new R1, and R2 is an unknown. And, so now we can just do the algebra. So, and I'll go ahead and do the steps here. So, it's moving 3,600 plus R2 times 15, moving this over here is 75 R2. Okay, just doing some algebra on this guy. And so now what do we do? Now I can factor in the 15, so 3,600 times 15 plus R2 15 equals 75 R2. Therefore, I'm getting a little scrunch down here in the corner. So now R2 is now, move this guy to the other side, factor out the R2, and then move the 15 and the 75 back, and so it's going to be 3,600 times 15 over 75 minus 15. It's going to be 900 ohms. Okay, and we have to solve for the power, right? Did we do that already? No, we didn't, but we weren't asked to. We were asked to resolve for R1 and R2 values such that neither resistor drew more than 1 watt. And we knew that R1 is going to have the higher power because that's what it had in the original circuit. So we solved that, and then we used voltage division to solve for R2, but we didn't solve for the power in R2. But you could, and you would see that it's going to be less than 1 watt. All right, but you could do that on your own if you want, just to double check. Okay, great. See you next time.